Hi, this is the demo for our W4H Toolkit. As detailed in the paper, the system operates in two modes. Here, we showcase its operation on a local machine using the provided Docker image. To run the system, we simply pull the latest W4H Docker image from our publicly available Docker repository on Docker Hub and run it. After running the image, we provide tutorials on how to configure and use the W4H Toolkit. The system configuration is very straightforward. User needs to download a YAML configuration file and add their own PostgreSQL connection credentials. Customizations on which time series and geotables are needed in the system can also be done in this step. We have already customized a configuration file, which we drag and drop to apply it to the system. Next, we log in to ensure authorized access. The W4H Toolkit makes user access management easy and straightforward. Now, we'll show how to use W4H Import Hub to quickly set up a W4H database instance called DemoICDE, creating the GeoMTS tables as outlined in the configuration file. We use GeoMTS as a unifying format to acquire, store and analyze data from different wearable devices conceptualized as geographically tagged multivariate time series. pgadmin shows the tables have been successfully created. Now, let's select this new instance and import some offline datasets from Microsoft Band and Fitbit that we have collected previously. Each dataset includes a subject CSV file, which specifies the attributes for the subjects the data belongs to. Here, we have an example from Fitbit's subjects data. Here are the columns present in this file. Let's proceed to import this data. Done. Now, let's repeat the process for the Microsoft Band subjects data. Excellent. Now, let's proceed to import the time series data for each of these datasets. W4H comprehensively ingests both subjects data, detailing user information, and time series data, displaying wearable recordings for each device, to seamlessly integrate wearable data into GeoMTS tables. To integrate the time series data, the toolkit requires a mapping between the CSV columns, which can vary significantly across different wearables, and the W4H GeoMTS columns. Our tool automatically attempts to create this mapping based on the similarity of CSV column names and GeoMTS table columns, as demonstrated here. However, should adjustments be needed, users can easily modify the mappings. We have successfully imported the Fitbit time series data. Now, let's repeat the process for the Microsoft Band recordings. Despite the vastly different CSV columns, the W4H Import Hub can effortlessly find a mapping and import this file as well. Great, data from two different wearables has been imported. Now, let's explore offline analytics on the stored GeoMTS data. On the query page, we select the created W4H database instance. First up, specifying subjects to monitor. We'll use IDs to select 3 subjects from the Fitbit data we imported. We could select the subjects based on attributes such as age range as well. The toolkit also compares the selected subjects to a control group. This control group can be the entire dataset or filtered by IDs or attributes. For comparison, we'll use control group as individuals aged 25 or older and between 5 feet 6 inches and 7 tall. Moving on, we set the analysis period from August 1st to August 14th, 2016. The toolkit allows analysis of recurring time slots. For example, analyzing daily workout sessions from 6:45 to 9:30 and 12:30 to 1600 hours across the selected date range, which can easily be customized. Now onto the results. First up, we see subject trajectories during the selected dates on the map. The dashboard also provides aggregate stats like average heart rate and calories across subjects, with delta values showing the difference from the control group. Next, the heart rate plot visualizes heart rate time series for subjects, marking outliers in red and a safe heart rate range in green based on overall population stats. We also have line plots for calories and METs. The dashboard compares aggregate stats like average heart rate between selected subjects, blue, and control group, green, in bar charts, and also shows stats for the selected time slots. Lastly, the toolkit allows exporting the selected clean GeoMTS data for both subjects and control group for further analysis. On to the next scenario, showcasing the toolkit's real-time data ingestion and analytics capabilities. We'll use StreamSim to simulate real-time data from the offline GeoMTS data, starting August 1, 2016, at 13:45. For real-time analysis, we're also interested in the most recent data, so we'll set the window size to the last 2 data points, representing the most recent 2 hours. Since the offline data is low frequency, we'll speed up the simulation with StreamSim, making every hour equal to 1 second, to test the system's real-time capabilities. In the results, we see real-time updates to trajectories and stats every second, reflecting data ingested and analyzed in real time. The recent window stats and the comparison between subjects and control group are also updated in real time. Next, the heart rate plot, calories, and METs are updated in real time. Notably, MET values are computed on the fly using real-time calories and subject weights, not stored. The comparative bar charts update in real time too. The GeoMTS data remains exportable and is updated in a tabular format in real time. The toolkit also identifies heart rate outliers in the streaming data and adjusts the safe heart rate zone, green zone, based on the most recent population heart rate stats. The blue bar denotes the recent 2-hour window selected in the query time. The code and pointers to the Docker image of the end-to-end toolkit can be accessed through our GitHub repository. Thank you for your time.